At the heart of the AI boom is a machine that has to hit a moving drop of molten tin with 2 laser pulses, not once, 50,000 times every second. The first pulse flattens the drop. The second turns it into an exploding ball of plasma. That flash creates a kind of light you cannot make with an ordinary lamp. And without it, the smallest layers of advanced chips become much harder to manufacture. This is EUV lithography. It does not make a chip by itself. It prints the most intricate layers on one. The process starts with a drop around 25 microns wide, fired through a vacuum chamber at 70 meters per second. Why go to this absurd length? Chip makers use light, like an unimaginably precise slide projector. Normal deep ultraviolet lithography uses 193 nanometer light. EUV uses 13.5 nanometers, more than 14 times shorter. Shorter light can resolve finer detail. But EUV comes with a trap. Air absorbs it. Glass absorbs it. The normal tools of optics simply stop working, so the entire exposure path has to happen in vacuum. And instead of ordinary lenses, the machine uses mirrors. That is why the tin drop matters. In ASML's laser-produced plasma source, a gentle pulse first shapes each moving drop into a tiny pancake. A stronger second pulse vaporizes it into plasma. The resulting burst emits EUV light. Making that trick work once is science. Making it work 50,000 times a second is industrial engineering. Cameras, sensors, lasers, and vacuum systems must agree on where a drop will be, and exactly when. A missed shot means lost light, lost time, and eventually lost wafers. The light then travels through a chain of mirrors, past a patterned mask, and onto a silicon wafer. At the far end, the wafer stage moves beneath the light with extraordinary control. ASML says it stage checks and adjusts 20,000 times per second, while robot arms transfer wafers through airlocks at positioning accuracy measured in microns. The next version of this machine is called High-NA. Established EUV works at a numerical aperture of 0.33. High-NA raises it to 0.55, collecting light across a wider angle. Wider angles mean finer patterns, but they also make the physical machine bigger. Zeiss says the projection optics for High-NA contain more than 40,000 parts and weigh around 12 tons. The illumination system is about 6 tons more. Resolution gets smaller. The machinery required to achieve it gets larger. ASML says its XE5000 system can provide 8 nanometer resolution. Compared with the earlier NXE generation, that means features 1.7 times smaller and transistor density 2.9 times higher. The challenge is not simply to make a brighter light. It is to make every mirror, stage, mask, and wafer agree at the same scale. And this is not only a laboratory experiment. On March 18, 2026, Imec announced that ASML's XE5200 High-NA system had arrived in its 300mm cleanroom. Imec expects the system to be fully qualified by the fourth quarter of 2026. The machine is not one invention. It is a vacuum system, a plasma engine, a laser orchestra, a mirror factory, a moving wafer stage, and a cleanroom installation, all forced to act like one instrument. Its value is more physical than magical. It gives tomorrow's chips a way to fit more useful work into the same piece of silicon. So the next time an AI model answers in a second, remember the strange beginning of that computation. Somewhere upstream, a tiny drop of tin was fired through a vacuum, struck twice by light, and turned into a brief artificial star. For more stories about the machines beneath the digital world, subscribe. They never sleep.